In this section, we're going to talk about another method we can use for finding the volume of a solid of revolution. And there are some solids that we could use either method to find the volume. And then there are others where one method is definitely going to be easier over the other one. And sometimes the most difficult things for students is to decide what method they should be using. So it's really important to understand the similarities and the differences between the two methods. So before we go into any formulas or examples, I want to first kind of give you the background of how we're going to do volume by shells, and then do a little comparison chart of some things we talked about in the volume by slices, and how they might be either similar or different in this section when we do volume by shells. So with volume by shells, again, we're going to be given some two-dimensional region, and we're going to be asked to revolve it around one of our axes and find the volume. So these are still volumes of revolution. So let's say this top boundary is f of x. It goes all the way down to the x-axis. And I've got this one from 0 out to just some random a value. So we're going to revolve this around the y-axis. So we've got our original two-dimensional region here. And when we revolve it, just like with the other method, when we get to 180 degrees, we are going to have the exact replica of it on the other side of our axis of revolution. And when we get to 360, it'll be back where it started. And we'll have these circular cross sections. So from the outside, this one's going to look like a cylinder. But when we look inside, there's a little bit of a bowl kind of scooped out of it, but it doesn't go all the way to the bottom. This bottom part here is solid. The bowl part only goes about halfway down. So we want a way to figure out how to find the volume of this function. And this one would be pretty difficult to do with the disk method. And that's because if you were to do perpendicular slices, now I'm going to erase these in just a second, but if you were to try to do perpendicular slices, if you remember in section 6.2, we had to make sure that the top function always stayed the top function and the bottom function always stayed the bottom function. And that is still always true. Everything we learned in section 6.2 is still valid. And if you look, there are certain slices of this region, if we go perpendicular to our axis of revolution, where the outer boundary is x equals a, and then the inner boundary is the function. And then if I go a little bit farther down and do a slice perpendicular to my axis of revolution, the outer boundary is a, but the inner boundary is 0. So the bottom function changes. So if we wanted to do this using volumes by slicing, we would actually have to break it into two pieces right there where that bottom boundary changes. We would have to do this as two different integration problems and think of it kind of as two different volumes and find their volumes individually and add them back together at the end. That's if we used the disk method. Now with the volume by shells, this is going to be much easier. So I'm going to draw this again so that we can see what exactly about the shell method is going to be different. So we've got almost this parabola shape, and we connect it down to the x-axis. Same exact region, still rotating it around the y-axis. And we get these circular cross sections. So we're trying to make it look three-dimensional when we do that. One of the main differences with the shell method is when we do our slices, we do them parallel to the axis of revolution. Excuse me. So since my y-axis is my axis of revolution here, which is a vertical line, I'm going to take my slice also to be vertical. And if you follow what happens to that slice as it rotates around the y-axis, you're going to have a copy of it on the other side. And that one in particular slice will have a circular shape. Now we can look at another slice, maybe up here, parallel to our axis. We would have a copy of it on the other side, and if we followed what happens to it as we rotate it, it would have circular cross sections. So we see that one's got a little bit bigger of a radius because it's farther from our axis of revolution. It's also a little bit taller because we're using the function here for height, and the function has a bigger y value there. So it's a little bit wider, the radius is bigger, and it's a little bit taller. So with volume by shells, what we're really doing is we're going to take our solid that we've created and we're going to slice it up three-dimensionally into these cylinder shapes, these really, really thin-walled cylinders, kind of like soup cans. If you imagine taking the top and bottom off the soup can. Some of the soup cans are short and fat, some of them are tall and skinny, or vice versa, depending on the function that you're using. And then we nest them all back together to create the solid. So if we look at like the surface area for each of those soup cans, the surface area of each one, and then add them all back together, are technically the volume for each of the soup cans, because the thickness, again, we're going to call dx. So really it technically is going to be a volume. If we take the surface area and then multiply it by the thickness, it will give us a volume. The thickness is dx. So the formula for volume using shells looks a lot more like a surface area formula for a cylinder. So just from geometry, we know that volume of a cylinder is 2 times pi times the radius times the height. Those are two things that we just noticed in this example up here between the black cylinder and the green cylinder, that there were two differences that we're going to have to account for. The radius on the green cylinder is larger than the radius on the black cylinder. So that's going to be something that has variables. Also, the height of the green cylinder it's taller than that on the black cylinder. So that also, the height is going to have variables. And again, these are circular, so we've got the pi in there, but we're not dealing with area of circles, we're dealing more with surface area of cylinders. So that's where the 2 pi comes in, because we're basing this off surface area of a cylinder, and then times the thickness, which is the dx. So if we were able to do this for an infinite number of cylinders, break up the entire interval from 0 to a into cylinders, and find all of their volumes and add them all back together, we would end up with the integral from 0 to a of 2 pi times a radius function and a height function and the thickness of your cylinder. That's what gives it the volume. This is going to be the volume of all those little cylinders from 0 to a added together, which will give us our total volume. The nice thing about shell method is there's not anything special that you have to do for hollowness. it will just kind of naturally play into this formula. And then also dealing with different vertical axes of revolution is also really, really easy to incorporate into this formula. Notice that the example I gave you is around the y-axis, but I wrote my integral in terms of x. That is one of the main differences with the shell method. And we've already mentioned one of them, so let me write both of them down. Our slices are drawn parallel to the axis of revolution. So with discs, when they were perpendicular and we spun them around, it created a circle or a disc with this little bitty thickness. Now, if we take them parallel and we spin them around, they actually turn into these cylinders, these empty cylinders with a tiny little bit of thickness. So our slices, when we use the shell method, are drawn parallel to the axis of revolution, and also our integral is set up with the variable opposite our axis of revolution. So one nice thing about the shell method is we can do all of these y-axis revolutions with the shell method and never have to rewrite our functions in terms of y. We can leave them all in terms of x. Because if we're going around the y-axis, the shell method is going to want us to use x's, because the integral is set up using the variable opposite the axis of revolution. And when I say opposite, our only choices are x and y. So same means x and x. Opposite means if you're going around y, use x. If you're going around x, use y. So these are two main differences that we're going to see with the shell method, besides just the formula being a little bit different. So the height function that we see here, we get just by looking at our slice. Now that height function can go from the given function all the way down to the axis, or it can go between two functions, and we could have to do some sort of subtraction problem and say like a top function minus a bottom function. And we'll look at an example of both. The radius function, there could be several options, and the radius function could change, and that's where we're going to account for our other vertical axes of revolution. So I want to first explain to you how we're going to deal with some different radius functions. For your radius function, there are two things you need to look at. We are going to let x represent our region that we just drew. The letter x, the variable x, is going to represent the region we just drew. And the reason we're letting that equal a variable is because our region spans multiple x values. So we don't want to just assign it a single number. Those multiple x values that it spans are going to be represented in our limits of integration. So this variable x is in there to represent that there's a whole span of x values that our region is going to use. The other thing that we need to know when we figure out our radius function is what our axis of revolution is. So if it's the y-axis, it could equal x equals 0. Or we could have x equals some other number. But but this is our axis of revolution. We need these two pieces of data, and we need them, it's nice to have them drawn. Figuring out your radius function is going to be a lot easier if we actually have them drawn on a graph. These are the two things you need to look at: where your region is situated and where your axis of revolution is situated. And you're always going to do, to figure out your radius function, you're going to do the one on the right minus the one on the left. Right minus left. So you might be doing region minus axis, or you might be doing axis minus region. So I want to show you a couple of quick examples. These are not going to be full volume problems, but just examples on how that radius function could be set up a few different ways. So let's say this is our region, and we're going to revolve it around the line x equals 5. Now for the region, we always use x because it spans multiple x values here. So we've got two things drawn on the graph. I've got my region drawn, and I also have my axis of revolution sketched. To figure out the radius function, we're going to do the one on the right minus the one on the left. So the one on the right is x equals 5. So I'm going to say 5 minus. And then the one on the left is the region. And that region is not just one single x value, it spans a whole bunch of x values. So 5 minus x. So on this one we did axis minus region, and that's because the axis is on the right and the region is on the left. So another example, there's our region that we're being asked to revolve, and we're being asked to revolve it around x equals 1. So the region is always going to be symbolized by an x in our radius function. And when we set up that radius function, we're going to do the one on the right minus the one on the left. So in this graph, the region is on the right, and the axis of revolution is on the left. The axis of revolution is always going to be represented by just a number. So this is x equals 1. So our radius function is going to be x minus 1. I want to show you two more really quickly. I didn't show you just the most simple basic one, and that is we've got this region here, and we're going to revolve it around the y-axis. So you need to think about what the equation for the y-axis is, because we need a number representation for that if we're going to do right minus left. So the y-axis has the equation x equals 0. So the region is always represented by an x, and then our axis of revolution here has a value of x equals 0. So our radius function is just the one on the right, here the region is on the right, minus the one on the left, which is the axis. So the simplest, most basic radius function is just x. And that's when your region is on the right and you're going around the y-axis. Then all you're going to use is x as your radius function. And then one more real quick, and I'm sure you can figure out exactly what we're going to do with this one. So here's our region, kind of strange looking. And we're going to revolve it around x equals -3. Remember, our region is x. And if we wanted to set up a radius function for this, do right minus left. So the one on the right is the region. And then subtract the one on the left, and that's the axis of revolution, which has a value of -3. This one's actually going to turn into addition, because we're subtracting a negative. So that's a possible as well. So make sure, in order to decide your radius function, you have your original two-dimensional region drawn, and you also have your axis of revolution sketched in there, because to decide your radius function, you want to do the one on the right minus the one on the left. And that takes care of your radius function. Now, this might create some hollowness if your axis of revolution is not being used as one of your boundaries. We don't have to do anything special for that. We don't have to do anything differently. So it's not like the disk method where we had this separate washer method we had to learn for hollowness. Don't need to worry about that with shell method. So that's nice. We also don't have to worry about shifting anything. Really, this doing this right minus left is what does the shifting for us. So like I said earlier, the formula here is just based on volume of a really, really thin-walled cylinder. So the thickness of the wall is the dx, and that's the thickness of each individual wall. And then the surface area is 2 pi RH. And if we do this for every single cylinder that's going to fit and make up our three-dimensional volume and add them all back together, we will get an answer for the entire volume. And we're going to look at a couple of examples in just a minute. But I had mentioned we're going to make a little table of some main differences between the disk/washer method and the shell method. You are going to have to decide when you see these problems which way you're going to do it. It's not going to necessarily say in the instructions, find this volume using the disk method, find this volume using the washer method, or find this volume using the shell method. It's just going to say, here's a region, revolve it around this axis, tell me what the volume is. And you have to look at the information that you're given and decide which method to use. So one of the differences we've already pointed out is that when you do the disk method, you're going to use the variable that matches the axis of revolution. So the integral is set up with the variable that matches axis of revolution, where the shell method is set up with the variable that's opposite. So for this one, variable matches. For this one, variable is opposite. So for most problems, especially in algebra, when we're given functions, functions are given to us in terms of x. Because of that, the disk method because we're going to use the variable that matches the axis of revolution, we're going to use the disk method mainly for x-axis or other horizontal line rotations. And I say horizontal because the x-axis is horizontal. So any other horizontal line we can shift up or down to match up with the x-axis. Since the disk method uses the same variable as the axis of revolution, when we go around the x-axis and we use the disk method, we can keep everything in our integral in terms of x. That will allow us to keep everything in terms of x, which is usually just the natural way that functions are given to us. On the other hand, with the shell method, we do the variable opposite the axis of revolution, which means y-axis or other vertical line rotations. We'll use the shell method. This again will allow us to keep everything in terms of x because the shell method is going to get set up with the opposite variable. If we're going around the y-axis, then shell method will be set up in terms of the opposite variable, which is x. So if we stick to this rule and we remember this rule, this is a really, really good rule that should work every single time. That if you always use disk method for x-axis rotations and shell method for y-axis rotations, 99% of the time you'll be good to go. So a couple of others just for like studying purposes. With our disk method, our slices are perpendicular. To the axis of revolution. And then when we spin them, that's how we create the disks. With the shell method, our slices are parallel. And when we spin that, it makes a really thin-walled cylinder. The disk method is based on area of a circle, which is pi r squared. So that's why inside of the disk method formula in our integrand we see pi times the radius function squared. But our shell method formula is based on surface area for a cylinder, which is 2 pi rh. That's what we see inside of our integrand. And I'm sure there's lots of other little things that we could point out. These are the most important. These are the most important if you get stuck on a problem and you have no idea where to even start. You always start with a picture of your two-dimensional region, and then you can reflect it and give it those little arcs to make it look three-dimensional. And then I would then say, well, am I going around the x-axis or the y-axis? And that will tell me if I should use the disk method or the shell method. And then we'll at least have a basic formula to go from there. So let's look at a couple of problems that use the shell method. We're going to find the volume of the solid of revolution that's formed when the region bounded by y equals 2, y equals x squared plus 2 and x equals 1 is revolved about the y-axis. So let's start with a picture of our region. Start with a picture of the region. Y equals 2 is just a horizontal line. X equals 1 is a vertical line. And then y equals x squared plus 2 is a parabola. It goes through the point 0, 2. And then if we plug in 1, we get 3. And if you connect them, this is the region that ends up being enclosed. Now, y equals x squared plus 2 does extend to the other side, but nothing is going to get enclosed on the other side. We need that x equals 1 to help us actually enclose something. And we're going to revolve this about the y-axis. So 180 degrees will give us the reflection. And then 360 will take us back around to where we started. On the outside it looks like a cylinder, but if you look inside, there's a bowl shape carved out of it. Since we're going around the y-axis, I'm going to use the shell method. Just automatically, that's the first thing I'm going to try. Because it's around the y-axis, I'm going to use the shell method. So remember, we're going around the y-axis, which has an equation of x equals 0. Let's start with our radius function. We need a radius function. So here's our region. And our radius, or our axis of revolution, is x equals 0. For the radius function, we want to do right minus left. So I have my region drawn on the right, and my axis ended up on the left. So my radius function is just x. If you draw your slice, and remember slices are parallel to the axis of revolution, the slices here, they go from the parabola right here down to the y equals 2 line. So our slices have a top function and a bottom function. So I'm also going to set up a height function, which has a top and a bottom. So we're going to do top minus bottom. On the top, we've got x squared plus 2. On the bottom, it's just y equals 2. So your height function might have a top minus a bottom. And in this case, it does. And if we simplify that a little bit, the plus 2 and minus 2 are going to end up canceling, which is going to leave us with just a height function of x squared. So these are the pieces that we need to set up our integral. We've got our radius function and our height function. So with the shell method, we do 2 pi times your radius function times your height function. And everything here is in terms of x, because the shell method uses the variable opposite your axis of revolution. our axis of revolution is the y-axis, so we're writing everything in terms of x, and that is going to include our limits of integration. Those have to be x values as well. So look to see how far to the left the region goes, and that's 0, and how far to the right the region goes, that's 1. So we're going to be integrating from 0 to 1. So we'll clean this up just a little bit. I'm going to go ahead and pull the 2 pi out. Those are just coefficients. We can deal with those at the end. Anything with variables has to stay inside because we have to apply our antiderivative rules to it. X times x squared is x cubed. And we want the antiderivative of x cubed, which is 1/4 x to the 4th. And we need to evaluate it from 0 to 1. So if we plug in 1, we just get 1/4. If we plug in 0, we get 0. So we need to do 2 pi times 1/4, which ends up being pi over 2. So our volume there about the y-axis is pi over 2. And we'll look at one more, and this time we'll use a different axis of revolution. Let's find the volume of the solid. Of revolution formed when the region bounded by y equals cosine x, y equals 0, and x equals 0 is revolved about x equals pi. So a little trigonometry inside of our calculus. This will be fun. Definitely something we need to see because it's definitely going to come up. So first of all, everything you do with trigonometry needs to be in radians, especially when you graph. It needs to be in radians. So let's take a look at the y equals cosine x graph. The cosine graph is the one that starts up at its amplitude and then goes from there. We also want to use the y-axis and the x-axis. So here's the y-axis. Here's the x-axis as boundaries. So it looks like this is our region. They didn't give us an interval to work with, so we've just got to rely on intersection points. So you also need to know where the cosine graph intersects our x-axis here, and that's going to happen at pi over 2. And that's a unit circle value. We do need to know all of our unit circle values from trigonometry. So I'm going to get rid of some of this other stuff. It's just going to get in our way now that we know that we don't need it for this problem. So we've got our region. Let's say here's pi. That's where our axis of revolution is going to be. That's where we want to revolve around. So I need to take my yellow shaded region there and revolve it around the line x equals pi. So at 180 degrees, I will have a reflection over pi. And it's going to be, all my points are going to be equal distance. So from pi over 2 to pi is a distance of pi over 2. So that point is going to translate to a distance of pi over 2 to the other side, which is 3 pi over 2. This 0 point is pi units away from pi, so it's going to translate to another pi units to the other side, which is 2 pi. So there's my base. I know my height is perfectly vertical here. And then we have our cosine shape. And we'll give it our circular cross sections. Draw your little arcs. And on the top I like to draw a circle. From the outside it looks like a cylinder, and a lot of them are going to. But this thing is hollow in the middle. It's got a hole right through the middle. You couldn't even, it's not even like our bowls where we could pour something inside. This one is completely hollow in the middle. It's kind of like a donut without the extra rounded sides. It's got squared off sides on two of the sides and just rounded on one of the sides. So remember, the original region was here. This was our original region, and that is important because to figure out our radius function, we're going to compare the original region to the axis of revolution. So for r of x, you're going to do whichever one is on the right. Do not worry about the reflection being on the right. We don't care about that at all. You look at your original region, which is x, and you look at your axis of revolution, which is x equals pi. And you're going to do the one on the right minus the one on the left. So here, the axis of revolution is on the right, the region is on the left. So we're going to do pi minus x for our radius function. For the height function, we need to draw our slice. So I'm going to come down through parallel to my x equals pi line. X equals pi is vertical, and I need to be parallel to that. So I'm going to draw a vertical slice through my region, and I need to know what the top boundary and the bottom boundary are. And this is typically going to be a top minus bottom. So on the top, I've got my cosine graph. On the bottom, I'm hitting the x-axis, which has an equation of y equals 0. So this means the height function, not f, sorry. Our height function is just cosine. So our volume, we've got 2 pi times our radius function times our height function that we want to integrate with respect to x. And then we need our limits of integration. So look back at your original region and see how far left and how far right it goes. So it looks like on the left it's 0, on the right it's pi over 2. So we're going to be integrating from 0 to pi over 2. Now, this is actually an integral that you probably don't know how to work by hand yet. If we pull this 2 pi out, we can't pull this one out because it's part of the pi minus x binomial that we have to distribute the cosine into. But if you actually take a look at this, this is not something that we have learned how to integrate yet. So if I distribute, this is pi times the cosine of x minus x times the cosine of x. Now the first piece I could integrate, because pi is just a number, we just want the antiderivative of cosine, which is sine. It's the second term here that's a problem. When I see a product of two functions of x, typically we're going to have to do a u substitution. The problem here is that these two functions are completely different, and a u substitution for one is not going to cancel out the other. Also, if you remember back to when we talked about integration by substitution, we're also typically going to see one of them is a composite function, and neither one of these is a composite function. So right now this is a problem. This is not something that we know how to integrate by hand. We will learn how to integrate that by hand this semester, but we haven't yet. So just not yet. So we're going to have to do this one in the calculator. So a couple things, if you've never integrated in your calculator, because this is a trig problem, we need to make sure that we're in radians. So under mode, go to your mode button and make sure that you are in radian mode. That's because pi over 2 is a radian angle. We're going to be plugging pi over 2 in for the x's, and x represents an angle on our cosine function there. So make sure you're in radian mode. And the way that you can integrate, or you can do definite integrals in your calculator, is by going to Math, option number 9. It says FNINT. We're going to be integrating a function, or function integration. Depending on your style of calculator or the age of your calculator, when you choose this, two different things might happen. If your calculator is newer, it'll pop up with an integration symbol on your screen and some empty boxes for you to just plug in what you need to plug in. Since we already have this all written out by hand on our paper, we know that in those boxes we're going to plug 0, pi over 2, pi cosine x minus x cosine x, and then dx. And don't forget, at the end, once we get our answer, most likely this is not going to be a nice rational number. So we also need to multiply that by 2 pi at the end. So don't forget that part. If your calculator is a little bit older, all it's going to do is put FNINT on your home screen in a parenthesis. So it still wants all of this information, but we just need to know the order to enter it. So you always enter your integrand first. That's the function that you're trying to integrate. And then you type in your variable. And then you type in your lower bound and your upper bound. And you separate them all with a comma, and there is a comma on your keypad on your calculator right above the 7. So for this particular problem, we would enter it as so. It would say FNINT when I selected Math 9, and then I would write pi cosine x minus x cosine x, comma, and then I would just say x because we're integrating with respect to x. That's what goes here. And then 0, comma, pi over 2, close parentheses, and hit enter. No matter what type of calculator you have, you will get the same answer. Once we get this answer, remember we have to multiply it by 2 pi because we pulled that 2 pi out in the front when we set up our integral, this 2 pi right here. Now, you will very soon know how to integrate this by hand, but for right now you don't. And I don't want to avoid all of these types of problems just because we don't know how to integrate them yet. As long as it's a definite integral, which means we've got limits of integration to plug in, our calculator will do it for us. So let's see what our calculator says, and I want you to try this as well with your graphing calculator so that we can make sure we get the same answer. If you do not get the same answer, try again, see if you can figure out what you did wrong. But if not, let me know. I can make a video on my desktop that actually pulls up a kind of a computer replica of our TI-84 calculator. I would have to do that from school though. So I'm just entering this in my calculator right now. So I've got 0 to pi over 2. Mine comes up with the integration symbol. And my integrand is pi times cosine x minus x times cosine x. I'm integrating with respect to x. And just the integration portion, I get 2.570796327. And remember, we still have to multiply that by 2 pi. So we just have an approximate answer this time, not an exact answer. We've got 16.153 approximately. Unless you know exactly what the value of 2.507 is, which I don't think it's going to have one. Let me see. I know it's got a pi in there. For right now, we're not going to be able to get the exact. We're just going to be able to do the approximate. So this one we have to do in our calculator. And really, any of the other ones you could do in your calculator as well. You don't necessarily have to work them out by hand. Most of what we're going to learn here in Chapter 6 with applications of integration, we're learning how to set up integrals to calculate new things. In Calculus 1, really the only thing we talked about as an application for definite integrals was area under a curve, area all the way down to the x-axis. So in Section 2, we found area between two curves, and then Section 3 and Section 4, we saw that we could also use integrals to find volumes of revolution. The tedious integration part of it, we're not so concerned with right now, even though it's good practice. Once you get that integral set up, the understanding of the setup in the integral is the most important thing. And then after that, it's really just doing the actual calculation of it. So this one we got 16.153. If you didn't get that and you're not quite sure what you're doing wrong, just let me know, and I can help troubleshoot, or possibly even make another video focusing more on the calculator and how to do this in the calculator.